Hi everyone. In today's online video lecture, we're going to continue the discussion of statistical inference by showing how hypothesis testing can be used to determine whether a statement about a certain attribute of a population should or should not be rejected. So, as we've covered earlier in the material, before hypothesis testing, we've established the fact that usually we don't have the data for the whole population, which is why we end up using a sampling process to collect data from a sample and then use the sample estimates in order to estimate what the values for the population would look like, and which is why we need to use hypothesis testing so that we can prove that the conjecture that we made about the population using the sample is in fact scientifically correct, and it was not just because of a sampling error or just by chance or by luck that we got that certain value. So in this section, we're going to conduct hypothesis tests using Excel and R both. But before that, I'm just going to go over some of the important calculations that we need to understand before actually using the functions in R and Excel to run those calculations. We're going to start off with the definitions of null hypothesis and alternate hypothesis. It's not usually always all obvious how the null and alternate hypothesis should be formulated, but it's a trial and error process. Learning to formulate hypotheses correctly will take some practice. You should expect some initial confusion about the proper choice of null and alternate hypothesis. The examples from the book chapter and whatever is posted on Canvas in class notes can help you learn and go through the process of developing a couple of null hypotheses till you actually understand how to formulate them correctly. So in the introduction to this section, we stated that the null hypothesis is a tentative conjecture or a statement about a population parameter, such as the population mean or the population proportion. The alternate hypothesis, on the other hand, is a statement that is the opposite of what is stated in the null hypothesis. In some situations, it's easier to identify the alternate hypothesis first and then develop the null hypothesis. In other situations, it's easier to identify the null first and then develop the alternate. So as you read through the examples in the book, it will be clearer to you that it's not an exact process. You don't have to calculate the alternate first and the null second or vice versa. It depends on the context of the situation. Care must be taken to structure the hypothesis appropriately so that the testing conclusion can provide the information to the researcher or the decision maker, which will actually make a difference. The context of the situation is very important in determining how the hypothesis should be stated, and all hypothesis testing applications, all of them, they involve random sampling and using sample results to provide enough evidence to draw a conclusion about the whole population. So the null and alternate hypothesis, depending on how you formulate them, they can fall under one of the two categories. The first one is called a one-tail test, and the second one is called a two-tail test. So on this slide over here, what you see is three different types of null hypothesis. The first two types here are one-tail tests, and the third one is a two-tail test. The reason why it's called one-tailed and two-tailed is on which side of your distribution is the rejection tail. So as you can see in this first situation, where the null hypothesis is that the population mean mu is greater than some hypothesized value mu 0. Now, this is a conjecture or a statement that we're making that the population mean will always be at least this value mu 0. If this is not in fact true, the alternate will be true, which is that the population mean is less than this hypothesized value of mu 0. The rejection region hence lies in the lower tail of the distribution. In the second scenario, the population mean is hypothesized to be less than or equal to the hypothesized value. So the rejection region lies in the upper tail of the distribution. And finally, in this third scenario, this is the case where we might not have enough information to make the conjecture whether the population mean is higher or lower than the value mu naught. So instead, we open the possibility of it being both higher or lower. So the alternate can be true even when the value of mu is not close to this hypothesized value of mu naught. Hence, the rejection region ends up being on both the tails of the distribution. Now, because we're working with samples in order to estimate population parameters, there could be cases when the sample is not a true representation or is an extreme value for the population and may not correctly describe or represent the whole population. So that's the case when you make a wrong decision based on hypothesis testing. So here in this table, there are 4 types of situations because of the hypothesis testing. Either the null hypothesis is true, and because of the test we end up not rejecting H naught, which means we made the correct decision and the correct conclusion. The same goes in this 4th case when the null hypothesis is not true, the alternate is true, and we reject the null hypothesis. That's also the correct decision. However, there are 2 cases where we might be making an error. The first case is when in fact the null hypothesis is true, but we end up rejecting it based on the sample. That's the case when we end up making a type 1 error. On the other hand, if the null hypothesis was not true and we did not reject it, instead we accepted it, we would be making a type 2 error. So both cases obviously we want to avoid, but depending on how severe the repercussions of each of those errors is, later on we'll see that we can adjust certain parameters in our hypothesis test so that we can avoid type 1 errors specifically, because that's the case when we end up rejecting an in fact true null hypothesis. We can reduce the probability of making a type 1 error by adjusting the level of significance of our null hypothesis. And by level of significance, what we mean is usually defining a percentage number at which we accept a certain decision from the hypothesis test. So when we're going to run the example in Excel and R, I'll go over what different level of significances will lead to in terms of the decision of the hypothesis test. But generally, the lower the level of significance is set, the lower the probability of making a type 1 error. In order to perform a hypothesis test, first we need to collect a sample from the population that we're testing for. Then we need to determine what is the population parameter that we're testing. Let's, for example, take the population mean as the parameter that we're testing for, and we want to use the sample mean to estimate a value for the population mean. Now, from the earlier slides in the chapter, we learned about interval estimation and the sampling distributions. So borrowing the same concept further, we're going to determine the test statistic for our hypothesis test using the sample data, and using this formula on the slide, formula number 611, in order to calculate the value for our t-statistic. The t-statistic, which is represented by this little t, is equal to the sample mean minus the hypothesized value of the population divided by the standard error of the sample, and the standard error is calculated as the standard deviation divided by the square root of the total sample size. So once we have all of this data from our sample, we can calculate the value of t-statistic and superimpose that over a student t-distribution in order to identify if that particular value for our t-statistic falls under the rejection region or not, and if it provides enough evidence for us to reject or accept the null hypothesis. So for this reason, we're going to use sample data that we collected earlier regarding coffee. This is provided in this Excel sheet called coffee test, and so the data that we have includes 36 observations about the weight of coffee. The context behind this example is that the Federal Trade Commission periodically conducts statistical studies designed to test the claims that manufacturers make about their products. For example, the label on the large can of Hilltop coffee states that the can contains 3 pounds of coffee. The FTC knows that Hilltop's production process cannot exactly place 3 pounds of coffee in each can, even if the mean filling weight of the population of all cans filled is 3 pounds per can. However, as long as the population mean filling weight is at least 3 pounds, the rights of the consumers will be protected. So the FTC's aim is that it finds a sample so that it can make the conclusion that the population mean filling weight of all the coffee cans is at least 3 pounds. We will show how the FTC can check Hilltop's claim that it fills it at least 3 pounds in each can by conducting a hypothesis test. The first step is to develop the null and the alternate hypothesis for the test. Let's assume that the population mean filling weight is at least 3 pounds. In this case, we will end up doing a one-tailed test and specifically a lower-tailed hypothesis test because we are setting up our null hypothesis to be the mean value greater than or equal to 3 pounds, and the alternate hypothesis being the mean value being less than 3 pounds. So in this Excel sheet over here, I have a sample t-distribution drawn. The assumed hypothesized value is 3 pounds, and the lower end of this distribution, this lower tail, is where our rejection region would be. Because if our sample test statistic falls in this rejection region on the left of this red line, then we can say that the rights of the consumer are not being protected, and Hilltop Coffee is making false claims that it fills its coffee cans with at least 3 pounds of coffee. So let's fill out these numbers here from the data that has been provided to us. The hypothesized value of this test is 3 pounds, so I'm going to put 3 in there. Our sample size is how many observations we have. So let's use the count function in Excel to count the number of observations, which is 36. And now we're going to use the data that has been provided to us from the sample in order to calculate the sample mean. And we can use the average function to calculate the sample mean. The sample mean turns out to be 2.92. The hypothesis test that we're going to perform today is to test if 2.92 is statistically far away from this hypothesized claimed value of 3 pounds or not. Is it just by chance that this value turned out to be lower, or is it because Hillstop Coffee is actually making false claims? And that's what we're going to find out today. For that, we have to calculate the t-statistic, but in order to calculate the t-statistic, we need some calculations before that. The first one is the sample standard deviation. So I'm going to use the standard deviation function in Excel to do that. Since this is clearly a sample, I will use the standard deviation .s. And next, we need to calculate the standard error, which would be the denominator for our t-statistic. And the formula for the standard error is the standard deviation divided by the square root of the sample size n. Now we have all the numbers to calculate the t-statistic, which is x bar minus the hypothesized value of the population mean, and we're going to divide this difference by the standard error. So the t-statistic for our test is minus 2.82, which falls on the left-hand side of our hypothesized mean. But we need to determine if this value is far enough from the hypothesized mean for us to conclude that in fact the null hypothesis is untrue and we should reject it. The degrees of freedom is defined as n minus 1, so it's equal to the sample size minus 1. And now we're going to use the student t-distribution. It's another distribution which mimics the normal distribution, but is more appropriate for smaller sample sizes. So we're going to use the t.dist function. The first argument that we need is the value of our t-statistic. The second argument is the degrees of freedom. And the final argument is if we are interested in a cumulative value or the density value. We're always, most of the time, we're interested in the cumulative value. So I'll press true or 1. And that should give me something called the p-value. The p-value is the probability, assuming that the null hypothesis is true, obtaining a random sample of size n that results in the test statistic at least as extreme as the one observed in the current sample. So in other words, this is the probability that you will find a value as low as this test statistic. And if our p-value is really small, it just proves that this t-statistic was not by chance. In fact, this is a common occurrence, and a value lower than this is hard to find. So we end up having strong evidence to reject the null hypothesis. So just as a rule of thumb, you should remember that the lower the p-value, the stronger the evidence against the null hypothesis. So as long as the p-value is really small, you have a very strong evidence to reject the null hypothesis and accept the alternate hypothesis. In this case, we have a really small p-value, which is close to 0.4%, and we can clearly say that we have to reject the null hypothesis. In fact, the alternate is true, that the Hilltop, the coffee company, is in fact underfilling its coffee cans. So if this was an upper tail test, we would have used another formula to calculate this number. And if this was a two-tail test, we would have just multiplied this probability by 2, because for a two-tail test, the rejection region would be on both ends of the distribution, so on both tails, which is why we multiply it. And if this was an upper tail test, we would just have to subtract this lower tail value from 1 in order to get the upper tail value. But in our case, since it's a lower tail test, the appropriate p-value is this first one, and we have enough evidence to reject the null hypothesis. Another way to make a decision rule is to set a level of significance, which we defined earlier as the probability of making a type 1 error. Normally, the commonly used levels of significance are 10%, 5%, or 1%, 5% being the most common. So if we set the probability of making a type 1 error as 5%, then the decision rule is that if your p-value, this number, is less than 5%, then we reject the null hypothesis. But if this p-value is higher than 5%, then we accept the null hypothesis. In this case, it's clearly lower than the level of significance is lower. We reject H0. And again, even with this second method of setting a decision rule, we end up rejecting the null hypothesis, and we can say that the claim that the company makes is in fact incorrect. Now we can perform the same analysis in R as well to get the similar numbers. Let's move on to R in order to calculate the same for our example. So I'm going to open up a new R script window, and here I'm going to write down the steps for hypothesis testing. Again, as a reminder, if I start a statement in R with a pound sign or a hashtag sign, R does not run the comment. Instead, it just reads it as a comment and doesn't do anything. So I'm going to label my script as hypothesis testing. In order to calculate the t-statistic, I first need to store some values, and obviously first I need to import my data set into R. So what I'm going to do is I'm going to move to my console, and here I want to name my new data set as coffee, and I'm going to use the read.csv file function in order to import my data set into R. Header is equals to true. Before you run this function, make sure that you have saved the CSV file that was provided under modules. I'll press enter, and now I can select where I saved this CSV file, and now the data has been uploaded successfully. R is calling it coffee. It has 36 observations of one variable, which we know is weight. So the next step is, the following steps are what I'm going to note down here under the script section, because I want to save the script file for later views so that I remember what were my steps in the functions that I used in hypothesis testing. I can also run the same functions here in the console, but that way it will not be saved. Running it in the script section is useful because I can store the script file as an R file and later on come back to this and check the functions and reuse them maybe with a different data set. So the first calculation that I need to make is to calculate the sample size. Obviously this was a small data set, so we already know that it's 36, but we just need to tell R what it is. So I'm calling this N, the sample size, and the way I can calculate it in R is if I count the number of rows in my data set. So I'll use the N row function in R over my data set called coffee. And if I select this part and run it, it's going to tell me that N is in fact 36. Next, I'm going to calculate the sample mean. And I'm calling this sample mean X bar. And I'll use the mean function in R. And I want to calculate the mean for the column labeled weight. And now I can select this and run this function. And here on the right hand side, you'll see the values being populated. So I know the sample mean now. The third calculation is for the sample standard deviation. Oops, I forgot to put the hashtag. Sample standard deviation. I'll call this value S, and the function is SD coffee $weight, and let's run this. The fourth calculation we need to make is, actually we need to tell R what our hypothesized value is. Let's call this hypothesized value as mu, and mu is set to 3. Oops, I forget this. The next calculation we need to do is to calculate the standard error. This is going to be used in the t-statistic formula, and I'll call this SE. And the way SE is calculated is that it's the standard deviation divided by the square root of the sample size. Now we have all the information to calculate the test statistic. I'll call the test statistic T, and the formula for T is X bar minus mu divided by the standard error. And now I'm going to tell R what my degrees of freedom is. I'm calling it df, and df in this case is n-1. And finally, now I have all the numbers to calculate my p-value. So let's call this p-val, and p-val, again, we can use the R functions, which are the equivalent of t.dist, and in this case it's pt because we're using a student t-distribution. The first argument is the value of the t-statistic, and the second argument is the value of the degrees of freedom. We can specify the lower tail being true, but even if we leave it out, R just assumes by default that it's true. So now I can I stopped running the statements after step number 3, so I can select the statements that I have together. R is going to perform the hypothesis test for me and store the values here, and I can see that the p-value is the same as what I got in Excel, 0.4%, and in fact that's less than this p-value is less than the most common level of significance, 5%, so I have sufficient evidence to reject the null hypothesis.